Hey everyone, my name is Kajal and welcome back to another video in the Webots tutorial series. Last week we learned how to make our custom two-wheel differential drive robot in Webots. This week we're going to learn how to write a controller code to drive your robot around. And to make it a fun, interesting project, we're going to learn how to drive a robot in a square or any polygon shape for the matter. If you're enjoying this Webot tutorial series, make sure to subscribe and hit the bell notification so you know every time I come up with a new tutorial. So without further ado, let's get into it. So go under Wizards and click New Robot Controller. Continue, and I'm going to write my code in Python, so I'm going to select Python. Continue. Let's call it Drive My Robot. Click Continue and done. And this is going to open the code in your editor here. Now it comes with the basic setup, which is great as it helps you remember some of the stuff. In Python, you can just write your code. You don't necessarily need to write a main. However, I prefer doing it. So let's just add a main. And I'm going to indent my code with a nice tab. So the first thing you do is create an instance of your robot, which is simply robot. Next is a timestamp. We are going to simply use 64. Next, as mentioned here, you need to create an object for your motors. So let's have a left motor, robot dot get motor. And then we can double check our names here. Under children, hinge joint, device, rotation motor, and you can see we've named our motor motor 1. Let's do the same for our second motor. Next, let's set the position for our motor to infinity and set the velocity to 0. Let's add a small comment of what we are doing and clean up rest of the comments we don't need. Next, we go into our main loop. As mentioned here, this is what your robot will do for every step in your simulation. This is a great place to read your sensor values, process them, and make decisions, which is usually give commands to your actuators like a motor, either by setting position or by giving velocity. In our case, we will simply give velocity. So let's clean this up. Because we're going to give velocity, let's determine a max speed. Which is 6.28. Let's have two speeds for our left and right motor. For now, let's run at half speed. Next, let's set the velocity to these speeds. And let's hit save. Now we go into our robot, and under controller we select the code we just wrote, which is drive my robot. And there we go, our robot is driving straight. For a differential drive robot, there are two ways to turn your robot around. Either stop one wheel or slow it down and let the other wheel go at the same speed, or turn the wheels around in different directions. So let's say you want to go left. You turn your left wheel backwards and you turn your right wheel forward. And in this way, your robot can take a left. So let's try that here. We'll change our left speed to negative and we'll keep our right speed to be positive so that it goes forward. Hit save and then play. Now as I flipped the left speed and right speed, we can see that the robot is now turning in the other direction. Now let's have both wheels at different speed and see what happens. As you can see, in the first case, the robot was turning in place. In this case, is actually going by taking a circle around a point. And this is a big plus of having a differential drive robot. It can nicely turn on the spot, as you must have seen with a Roomba robot. And when we reverse the speed, you can see the robot is now driving in the opposite direction. Here's an interesting question for you. How would you make the robot drive backwards? Tell me in the comments below. So we just learned how to drive our robot straight, but that's kind of boring. So let's do something interesting. Let's drive a robot around in a square, or in fact, a polygon of any shape. So let's get into the code. We're going to drive it around in a polygon shape. So let's decide the number of sides. For a square, that would be 4. Now let's also decide the length of our side. Our arena here has small squares of 0.25 meters. So let's go with that as the length side. Now our goal is to drive the robot from its starting position till the end of this corner. Now we know the speed of our robot and we know the distance. So let's just use time as an indicator of how long it should drive straight before it has to make a turn. One thing to note here, the max speed is actually angular velocity. So to compute our time to drive straight, we need to compute linear velocity. The formula is pretty simple. It's linear velocity is equal to wheel radius times angular velocity, which in our case is max speed. From our design, we know our wheel radius is 0.025. Now with this, we can compute the amount of time our robot should be driving straight along the edge of a polygon. It's going to be distance by linear velocity. So here's what we're going to do. Let's compute the start time. And then we'll compute the current time. Now if the time to go straight is over, then the robot should stop. Let's save and run our robot. As you can see, once it reached the other end, it stopped. Now similarly, let's compute the amount of time our robot should be turning. Let's turn on the spot at the vertex. So first, let's compute the angle the robot is supposed to rotate. For a square, it's going to be 90 degree, but let's make it general. So 360 degree divided by the length of our side. 360 degree in radians is going to be 6.28. Next, let's compute the rate at which our robot will turn. The formula is 2 times linear velocity divided by distance between wheels. From our modeling, we know the distance between the wheels is 0.090. Lastly, let's compute the amount of time our robot should be turning. So here's how we can think of our problem. From the start point till duration side, drive straight. Then after duration side till duration turn, and then go back to driving straight. Another way of thinking is keep driving straight unless you are in the rotation time period. If you're in the rotation time period, then rotate. Else continue driving straight. And this is what we are going to use. So if our current time is within the rotation time period, then you rotate. Else you drive straight. Now this time was computed for our first rotation. Accordingly, we need to keep recomputing our time for rotation for upcoming rotations. Let's save our work and see what happens. It's driving straight, turning, and then turning again. As you can see, it's following the square. During the next turn, you can see that it's drifted away a little bit and now it's sort of going in a diamond shape. And it represents real world in the sense that in real world, it's usually wheel slippage, uneven floor size, or something of that sort. To fix this, you probably need to have some sort of a feedback mechanism. We can see how the robot is driving, but the robot itself doesn't know where it's going. And this is what's called an open loop system, where you're essentially just sending in commands, but the robot itself has no idea about its own state or the environment. To correct our action, we need to actually send the signal back so the robot can update its states, so that it can know that it's drifted off its location and it can do a corrective action to come back into its system. And that is what we call a closed loop system. And that is something we can explore in one of our future tutorials. I hope you liked this video, so make sure to hit that like button, and if you haven't already, don't forget to subscribe. Also, if you have any questions or doubt, feel free to put them in the comments below. Thank you for watching, and I'll see you in the next video.